What if I told you that every technological breakthrough you've ever witnessed, every smartphone, every rocket, every quantum computer, is moving at a pace so glacially slow compared to the fundamental laws of physics that it's almost embarrassing? We live in an age where we can sequence the human genome, split atoms, and peer into the cosmic microwave background radiation from the birth of the universe itself. Yet here's the unsettling truth. The gap between what the laws of nature permit and what human technology can actually achieve is so astronomically vast that it should humble us. We think of ourselves as living in an era of exponential growth, of radical innovation, of unprecedented speed. But when you examine the fundamental limits imposed by quantum mechanics, when you consider the velocities dictated by relativity, when you contemplate the energy scales at which the universe truly operates, you begin to realize something profound. We're barely scratching the surface. The speed of light, the Planck scale, the quantum foam. These aren't just abstract concepts in textbooks. They're the universe showing us just how much faster, how much more energetic, how much more intricate reality can be. And we're still crawling. Think about the last time you marveled at a piece of technology. Maybe it was watching a SpaceX rocket land itself vertically after delivering satellites into orbit. Maybe it was holding the latest smartphone in your hand, a device more powerful than the computers that sent humans to the moon. Maybe it was reading about breakthroughs in artificial intelligence, quantum computing, or gene editing. In those moments, it's easy to feel like we're living in the future, like humanity has finally arrived at a point where our technological prowess is approaching something truly extraordinary. But let me offer you a different perspective, one that emerges when you look at our achievements not through the lens of human history, but through the lens of physics itself. When we talk about speed in technology, we're not just talking about how fast a processor can execute instructions or how quickly a rocket can escape Earth's gravity. We're talking about something much more fundamental. We're talking about the rate at which we can manipulate matter, the rate at which we can transfer information, the rate at which we can transform energy from one form to another. And when you start measuring these rates against the fundamental constants of nature, against the actual speed limits imposed by the universe itself, something remarkable becomes clear. We're not fast. We're not even close to fast. We're operating at a scale that is, from the perspective of fundamental physics, almost comically slow. Let's start with something seemingly simple. The speed at which information travels in our most advanced technologies. Right now, the fastest computers on Earth can perform calculations at speeds measured in exaflops. That is, quintillions of floating point operations per second. That sounds impressive, and by human standards, it absolutely is. But here's what you need to understand. The fundamental particles that make up those computers, the electrons flowing through circuits, the photons carrying signals through fiber optic cables, they're governed by quantum mechanics. And at the quantum level, particles don't just exist in one state or another. They exist in superpositions, in multiple states simultaneously, evolving according to the Schrödinger equation at timescales we can barely fathom. An electron in an atom, for instance, can transition between energy levels in femtoseconds. That's quadrillionths of a second. The fundamental vibrations of molecules, the oscillations that define the very nature of chemical bonds, occur on time scales of femtoseconds to attoseconds. An attosecond is to a second what a second is to about 32 billion years, longer than the current age of the universe. At these time scales, the universe is performing calculations, if you want to think of it that way, at rates that make our fastest supercomputers look like they're standing still. The universe itself is a computational engine operating at scales of speed and complexity that we can describe mathematically, but that we cannot even begin to replicate technologically. Now you might say, well, that's not fair. We're comparing human-made technology to the fundamental operations of nature itself. Of course, nature is faster, but that's precisely the point. The laws of physics set the ultimate speed limits, the ultimate efficiency limits, the ultimate capabilities of what's possible. And our technology, as advanced as it seems, is operating so far below those limits that the gap is almost unimaginable. We're like someone who has just learned to walk, marveling at their ability to move across a room, while the universe is demonstrating what it means to move at the speed of light. Consider the speed of light itself, approximately 186,000 miles per second. This is the cosmic speed limit, the fastest that anything, any information, any influence can travel through space. Einstein's special relativity tells us this isn't just a practical limit, it's a fundamental feature of space-time itself. Nothing with mass can reach the speed of light, and nothing, not even massless particles, can exceed it. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour at its closest approach to the Sun. That sounds fast until you do the math. That's about 0.06% of the speed of light, less than 1/10 of 1%. We've been working on rocket technology for nearly a century, and we've barely made a dent in approaching the fundamental speed limit of the universe. And it's not just about rockets. Think about communication. When you send a text message to someone across the country, that signal travels at the speed of light through fiber optic cables or as electromagnetic waves through the air. That's as fast as information can possibly travel. But here's the thing, even at the speed of light, there are delays. It takes light about 1.3 seconds to travel from the Earth to the Moon. It takes light about 8 minutes to travel from the Sun to the Earth. If you wanted to have a conversation with someone on Mars, depending on the planet's positions, you'd be waiting anywhere from 3 to 22 minutes for a response. The universe is so vast, and even the speed of light is so slow relative to cosmic distances that instantaneous communication across significant portions of space is simply impossible. The universe has built-in latency that no technology can overcome. But let's bring this back to Earth, literally. Let's talk about energy. Every technological advancement we've ever made has been fundamentally about harnessing energy and converting it into useful work. We learned to control fire, to harness the power of steam, to split the atom, to capture the energy of sunlight. Each leap forward in energy technology has enabled corresponding leaps in what we can build, where we can go, what we can do. But again, when you look at the scales of energy that the universe operates at, our achievements start to look modest. The Large Hadron Collider, the most powerful particle accelerator ever built by humans, can accelerate protons to energies of about 13 trillion electron volts. That sounds like a staggering amount of energy, and in terms of the energy contained in a single particle, it is. But here's a way to put it in perspective. The total energy in the Large Hadron Collider's beam, when you add up all the protons circulating in it, is about the same as the kinetic energy of an aircraft carrier moving at a moderate speed. We've built a machine 17 miles in circumference, buried it underground, cooled it to temperatures colder than outer space, and the total energy we're manipulating is equivalent to a large ship moving through water. Now consider what happens naturally in the universe. Cosmic rays, high-energy particles from space, regularly strike Earth's atmosphere with energies far exceeding anything we can produce in our accelerators. The most energetic cosmic ray ever detected, the so-called "oh my God" particle, discovered in 1991, had an energy equivalent to a baseball traveling at about 60 miles per hour, all concentrated in a single subatomic particle. We don't know what accelerated that particle to such enormous energy, but the universe did it naturally without any of the elaborate machinery we require. The universe is routinely performing feats of energy manipulation that we can observe, that we can measure, but that we cannot replicate. And then there's the question of scale. Our technology operates at scales that we can see, touch, manipulate with our hands or with machines we can build. We're extraordinarily good at working with objects that are millimeters to meters in size. We've gotten better at working at smaller scales. We can now manipulate individual atoms. We can build transistors that are just a few nanometers across. But the universe operates across a range of scales that defies comprehension. At the smallest scales, there's the Planck length, about 10 to the power of negative 35 meters. This is the scale at which quantum fluctuations in space-time itself become significant, where the smooth fabric of space and time that we experience breaks down into a quantum foam of uncertainty. We cannot probe this scale experimentally. We cannot build instruments that can directly observe phenomena at the Planck scale. The energies required would be so enormous that we'd need a particle accelerator the size of the galaxy. At the other end of the spectrum, there's the observable universe, about 93 billion light years in diameter. That's a scale so vast that light, traveling at the cosmic speed limit, hasn't had time to traverse the full extent of space since the Big Bang. We can observe distant galaxies, we can map the large-scale structure of the cosmos, but we cannot travel to these places. We cannot even send signals that would reach them within human timescales. The universe operates at scales that span some 65 orders of magnitude, from the Planck length to the cosmic horizon. Our technology operates comfortably across maybe 10 orders of magnitude. We're working in a narrow slice of reality, constrained by the scales at which we can effectively manipulate matter and energy. Let me give you another way to think about this. Consider computation, the processing of information. This is something we've gotten remarkably good at over the past several decades. Moore's law, the observation that the number of transistors on a computer chip doubles approximately every 2 years, has held roughly true for more than half a century. We've gone from computers that filled entire rooms to smartphones that fit in our pockets and are millions of times more powerful. But there are limits to this progress, limits imposed not by engineering ingenuity, but by physics itself. Every time a computer performs a calculation, every time a bit flips from 0 to 1 or vice versa, energy is dissipated as heat. This is a consequence of thermodynamics, specifically the Landauer principle, which states that erasing information requires a minimum amount of energy. In practice, our current computers dissipate far more energy than this theoretical minimum. But as transistors get smaller and more efficient, we're approaching these fundamental limits. At the same time, as transistors shrink, we're running into quantum effects. When components get small enough, electrons can tunnel through barriers they classically shouldn't be able to cross. The discrete nature of matter becomes unavoidable. We're reaching a point where classical computing technology is bumping up against the quantum nature of reality. Quantum computers offer a potential way forward, using the principles of quantum superposition and entanglement to perform certain calculations much more efficiently than classical computers. But even quantum computers face fundamental limits. They're subject to decoherence, the tendency of quantum states to interact with their environment and lose their quantum properties. Maintaining quantum coherence requires isolating quantum systems almost perfectly from the outside world, operating at temperatures near absolute zero. And even then, coherence times are measured in microseconds to milliseconds. The universe doesn't make it easy to harness quantum phenomena for practical computation. And here's something that might surprise you. There's a theoretical limit to how much computation can be performed by any physical system, regardless of how cleverly it's designed. This limit is related to the Margolis-Levitin theorem and the Bremerman limit, which together suggest that the maximum rate of computation is fundamentally limited by the energy available and the quantum mechanical constraints on how fast states can change. For any given amount of energy, there's a maximum number of operations that can be performed per second. And that maximum, while vastly higher than what we currently achieve, is still finite. The universe itself puts a cap on computational speed. Now let's talk about something that might seem completely different, but is actually deeply connected: Biology. Living systems are, in a sense, incredibly sophisticated technologies. A single cell is more complex than any machine we've ever built. It can replicate itself, repair damage, respond to environmental signals, convert chemical energy into useful work with remarkable efficiency. The molecular machines inside cells, proteins that act as motors, pumps, scissors, and construction equipment, operate with a precision and efficiency that engineers can only dream of. DNA replication, for instance, occurs at a rate of about 1,000 base pairs per second in humans, with an error rate of less than 1 in a billion base pairs per replication cycle. This is achieved by molecular machinery operating at the nanoscale in a warm, wet, chaotic environment. Our best attempts at nanoscale manufacturing require ultra-clean rooms, precise temperature control, and can't match the error correction capabilities of biological systems. Evolution has had billions of years to optimize these systems, to find solutions that work within the constraints of chemistry and physics. We're still trying to understand how these systems work, let alone replicate them. And consider the brain, the most complex structure we know of in the universe. The human brain contains roughly 86 billion neurons, each connected to thousands of other neurons through synapses. The total number of synapses is estimated at around 100 trillion. Signals in the brain travel as electrochemical impulses at speeds ranging from about 1 meter per second to 100 meters per second, depending on the type of neuron. That's far slower than the speed of electrical signals in a computer, which travel at a significant fraction of the speed of light. Yet the brain can perform pattern recognition, creative problem solving, and abstract reasoning in ways that our fastest computers still struggle with. The brain achieves this through massive parallelism, through the complex dynamics of networks, through mechanisms we're only beginning to understand. We're making progress in artificial intelligence, in building neural networks that can recognize images, translate languages, even generate convincing text and images. But these systems require enormous amounts of energy. Training a large language model can consume as much electricity as hundreds of homes use in a year. The human brain, by contrast, operates on about 20 watts, the power of a dim light bulb. In terms of energy efficiency, in terms of the ratio of computational capability to power consumption, biology is still far ahead of our technology. And this is after evolution has been constrained by the same laws of physics that constrain our engineering. Biology shows us what's possible when you have billions of years to optimize within physical constraints. We're still in the early chapters of that story. Here's another humbling fact. The universe is about 13.8 billion years old. Complex life on Earth has existed for perhaps 600 million years. Humans have been around for a few 100,000 years. We've had industrial technology for about 200 years. We've had computers for less than a century. In the grand sweep of cosmic time, our technological civilization is an eye blink. And yet, we already see signs that we're approaching fundamental limits in multiple domains. We're running into the constraints imposed by the speed of light, by quantum mechanics, by thermodynamics, by the discrete nature of matter. This doesn't mean progress will stop, far from it, but it does mean that the nature of progress is changing. The easy gains, the ones that come from simply making things smaller, faster, more powerful by brute force, those are becoming harder to achieve. Future progress will require not just better engineering, but deeper understanding of physics. It will require finding clever ways to work within constraints rather than simply pushing against them. It will require, perhaps, entirely new paradigms of technology that we haven't yet imagined. Consider fusion power. For decades, we've been trying to replicate on Earth what the sun does naturally, fusing hydrogen atoms together to release enormous amounts of energy. The sun does this through sheer brute force, through the immense gravitational pressure at its core that forces nuclei together despite their electromagnetic repulsion. We can't replicate those conditions on Earth. Gravity is far too weak at the scales we work with. So we try other approaches, using magnetic fields to confine plasma, using lasers to compress fuel pellets. We've made remarkable progress. Recent experiments have achieved net energy gain, more energy out than the laser energy in. But we're still far from a practical fusion reactor that can generate electricity for the grid. The engineering challenges are immense. The materials needed to withstand the extreme conditions, the precise control required, the sheer complexity of the systems involved, all of this makes fusion power a problem that requires not just incremental improvements, but fundamental breakthroughs. And fusion is still a relatively conventional technology, one that relies on known physics, on processes we can observe and measure. There are other possibilities, other potential technologies that push even further into the realm of physics we don't fully understand. Could we harness the energy of the quantum vacuum? Could we manipulate space-time itself to enable faster-than-light travel through mechanisms like warp drives or wormholes? These ideas exist in the equations of general relativity and quantum field theory, but turning them into practical technologies would require capabilities so far beyond what we currently have that they might as well be magic. The point I'm trying to make is this. When we look at our technology through the lens of physics, when we compare what we can do to what the laws of nature permit, we see that we're still at the very beginning of the technological journey. We're like the first organisms that crawled out of the ocean onto land, marveling at our ability to breathe air, unaware of the vast continents stretching beyond the shoreline. The universe has set the rules, has defined what's possible, and those rules allow for phenomena and capabilities that we can barely imagine. The universe can create black holes, objects so dense that they warp space-time into a one-way trap where not even light can escape. The universe can generate gravitational waves, ripples in the fabric of space-time itself traveling at the speed of light. The universe can create neutron stars, objects where a mass greater than the sun is compressed into a sphere the size of a city, where the density is so high that atoms as we know them cannot exist. These are not just curiosities. They're demonstrations of what physics allows, of the extremes that are possible within the laws of nature. Our technology is impressive by human standards. It has transformed our lives, extended our lifespans, connected us across the globe, given us unprecedented capabilities. But by the standards of physics, by the measure of what the universe demonstrates is possible, we're still operating at a pace that is, quite literally, astronomically slow. We're still learning the grammar of nature's language, still figuring out the basic vocabulary of what can be done. The universe is a master teacher, showing us through its phenomena what the laws of physics permit. And we're attentive students, slowly, painstakingly, building the knowledge and the tools to work within those laws more effectively. But make no mistake, we have a long, long way to go. The speed of human technology is slower than you think, not because we're not trying hard enough, not because we're not clever enough, but because the universe operates at scales of speed, energy, and complexity that we're only beginning to appreciate. And that's not a cause for despair. It's a reminder of how much there is still to discover, how much room there is for future generations to push forward, to find new ways of working with nature rather than against it, to gradually, incrementally close the gap between what we can do and what physics permits. The journey is long, but that's what makes it worth taking.